Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 7. Understanding Phi Sentences, the Pattern Library. Remember the language we are learning. There is one field, Phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When Phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are climbing book 10.1, Language Fluency. In our last session, you learned to read phi, to transform raw, noisy sensor data into a clean, honest map of the phase field, complete with its uncertainty. You cleaned the window. Now, we stand before that clear window, looking out at the landscape in motion. We have the letters. Today, we learn to read the words. We learn to recognize the common, coherent patterns, the clauses that make up the universe's dialect. This is the skill of the interpreter. You are in the observatory. The great telescope is focused, the lens is polished. Your first map of phi is projected before you, shimmering, evolving. Your job now is not just to see the light, but to understand the constellations. Scene, the living map. Return with me to the quiet laboratory. Our laser interferometer is still running, measuring the vibrating plate. But now, we are not looking at a single snapshot. We have a movie, a time series of phi of XY maps flowing across the screen. The landscape is alive. Ripples propagate from one edge. Certain regions seem to quiver in place. There's a persistent, swirling structure in the lower left that rotates slowly. And over there, a sudden, violent event where two dark points collide and vanish. In our last session, we would have seen only the terrain's shape. Now, we must understand its verbs. What is this landscape doing? What are the stories being told in the language of phi? This is our core puzzle. How do we move from seeing a beautiful, evolving phi map to actually understanding what we're looking at? We need more than a picture. We need a dictionary. We need to recognize that this smoothly flowing region is a jet, that this propagating ripple is a wave, that this swirling point is a vortex, and that this collision is a defect annihilation event. These recognizable patterns, these clauses, are the building blocks of reality's sentences. Learning to spot them is like learning to recognize grammatical structures. Here is a noun phrase, here is a verb, here is a prepositional clause that modifies the action. Let's step up to the observatory's main console. Our first tool is the derivative calculator. From our phi of XYT movie, we compute two new movies. 1. The time question movie, omega XYT. At each point and each moment, how fast is phi changing? This is the local rhythm, the tempo. 2. The space question movie, K, X, Y, T. At each point and each moment, in what direction and how steeply is phi changing in space? This is the local spatial pattern, the texture. These are not separate from phi. They are its first shadows. They are the echoes of change. And together, they form the basis of our clause library. Building the clause library, the universe's basic vocabulary. Imagine you're a linguist encountering an alien language for the first time. You listen, and you start to notice recurring sound patterns. A rising, falling tone followed by a click appears in contexts of greeting. A series of short, sharp bursts accompanies pointing. We do the same with phi patterns. Using our digital twin, our perfect sandbox, we generate pure textbook examples of fundamental clauses. We ask the twin, show us what a perfect traveling wave looks like in phi, omega, and k. It generates the data. We analyze it. We build a template. What does a wave clause look like? In phi, a series of parallel, evenly spaced ridges and valleys moving in a consistent direction. In omega, a constant, uniform value across the wave region. Every point oscillates with the same rhythm. In K, a constant uniform vector pointing perpendicular to the ridges. The spatial pattern is uniform. Crucially, for a true wave clause, omega and k are not independent. They are locked together by a constraint, the dispersion relation. For waves on a string, omega is long the k. For light in a vacuum, omega is called a ck. This relationship is the clause's grammar rule. A pattern that has wavy ridges, but where omega and k don't obey the system's dispersion relation, is not a coherent wave. It's noise pretending to be signal. Now, a smooth jet clause. In phi, a region where the phase increases or decreases steadily, like a smooth ramp or hill. In omega, nearly zero. The phase at a fixed point isn't oscillating, it's drifting steadily. In k, a strong, uniform vector pointing in the direction of the ramp. But, and this is key, the change of k, its spatial derivative, is negligible. The texture doesn't change within the jet, it's smooth. A defect clause, a phase singularity like a vortex. In phi, the phase swirls around the central point. If you walk a small circle around it, the total phase change is exactly plus or minus 2 pi, plus or minus 4 pi, etc., an integer multiple of a full turn. In omega, can be anything. The defect can be stationary or moving. In k, blows up at the exact center, the derivative is undefined, and forms a characteristic circular or spiral pattern around it. Our clause library holds these templates, mathematically defined. It holds their defining constraints. A wave must obey its dispersion relation. A jet must have negligible higher spatial derivatives. A defect must have integer topological charge. This brings us to our first coherence gate for understanding. Coherence criterion. A valid clause must exhibit internal consistency. Its measured omega and k must satisfy its own defining constraints within the bounds of measurement error. A wave where omega and k vary randomly and independently is not a wave. It's incoherent shimmer. Our dissonance indicator is now clear. A claimed clause that violates its own defining constraints is not a real pattern. It is incoherent noise that our pattern matching algorithm has mistakenly labeled a signal. It's like calling a random collection of letters a word. It may look vaguely like one, but it follows no rules of spelling or meaning. The safety rail is critical here. We must not be overconfident. Clause identification must be probabilistic. Our algorithm shouldn't shout, wave here. It should say, there is an 87% probability this region is a wave clause, a 10% chance it's a jet, and a 3% chance it's just noise. This confidence score is based on how well the local phi, omega, and k data fit the clause template versus a generic noise model. Where the fit is poor, confidence is low. We must report this uncertainty alongside our labels. If coherence breaks, we stop. If coherence returns, we continue. We cannot build understanding on misidentified clauses. If our confidence scores are uniformly low, if every wave is only 30% likely, then our interpretation is incoherent. We must go back. Perhaps our measurements are too noisy. Perhaps we need a different clause library for this system. We stop interpreting and we improve our reading. The coherence budget for interpretation. Before we start labeling clauses, we must assess our coherence budget. Do we have the capital to make reliable interpretations? Our budget here has two currencies. 1. Signal-to-noise ratio, SNR, in the derivatives. Calculating omega and k amplifies noise. A little fuzz in phi becomes a lot of fuzz in its derivatives. Our budget rule. To reliably identify a clause with confidence X%, the SNR of the relevant derivatives, omega or components of k, must exceed threshold Y. If the derivatives are too noisy, our clause labels will be random guesses. We cannot afford interpretation. 2. Temporal and spatial resolution. To see a smooth jet, we need our measurement window to be larger than the jet itself, but our pixel size to be small enough to see its smoothness. To catch a defect annihilation, we need our frame rate to be faster than the event. Our budget rule? The scale and speed of the clause must lie within the licensed window of our measurement's resolution and frame rate. If our budget is insufficient, we cannot interpret. We must earn more capital, average over more frames to reduce derivative noise, use a higher resolution sensor, or zoom out to see larger patterns. Our coherence gate, after interpretation, is the predictive power test. We don't just label and admire. We use our labels to make a specific, short-term prediction about how phi will evolve, and then we check if we were right. If we label a region as a smooth jet, we predict that in the next few moments, phi in that region will continue to increase or decrease linearly. We can use a simple Taylor expansion. Phi future is by phi now plus k doubly mine delta x plus omega delta t. If we label a pattern as a wave clause, and we've identified its dispersion relation, we can predict omega from k, or vice versa. If we see the spatial pattern, we can predict the temporal rhythm. It must have to be a coherent wave in this medium. If we map all the defect clauses, we predict that their total topological charge in a closed region is conserved, unless a defect pair is created or annihilated at the boundary. The pass-fail rule at this gate is quantitative. Does our prediction match what actually happens within the error bars? If our clause-based predictions are no better than just extrapolating the raw phi map or guessing randomly, then our clause labels are meaningless. They provide no understanding. We failed the gate. Our interpretation is incoherent. The rollback trigger is clear. If we fail the predictive power test, we revert. We discard the clause labels for that dataset or time period. We contain the error by marking that segment of data as uninterpreted. We go back to just reporting the raw phi, omega, and k fields with their uncertainties. We have exceeded our licensed window of interpretation. We must either improve our measurement, better budget, or refine our clause library. The triunity of a clause. Let's feel how triunity lives within each clause. A clause isn't just a spatial shape. It's a unified entity with time, space, and motion echoes woven together. Take our wave clause. Time echo, the constant rhythm, the periodic ticking at every point in the wave. Space echo, the uniform spatial texture, the parallel ridges and valleys. Motion echo, the phase velocity, v equals omega k, the speed and direction at which the pattern's shape moves. This isn't a separate thing. It's the relationship between the time and space echoes. A defect clause. Time echo, the defect's own rotation or drift speed if it moves. Space echo, the swirling or radiating pattern of k vectors around the core. Motion echo, the trajectory of the defect core through space, its world line. Every clause we identify implicitly makes claims about all three shadows. A misidentification will show up as an inconsistency between them. The prediction spine, from recognition to forecast. Our work builds a prediction spine, a set of testable claims that must hold if our understanding is sound. 1. Smooth jet prediction. Identifying a jet clause allows accurate short-term prediction of phi via linear extrapolation. The error of this prediction will be small and will grow slowly over time, linearly, as opposed to blowing up immediately. 2. Constraint clause prediction. Once we identify the governing constraint, like a dispersion relation, for a region, we gain predictive power with fewer measurements. If we measure k in a wave, we can accurately predict omega without directly measuring it over time. This is a reduction in degrees of freedom, a hallmark of true understanding. 3. Defect density prediction. Regions of high phase curvature, where del square phi is large, the phase landscape is tightly bent, will correlate with higher spatial density of defect clauses. The defects are the punctuation marks where the smooth narrative of phi breaks down. They naturally occur where the story is most contorted. These are not just observations, they are requirements. If these predictions consistently fail, our clause library is missing something fundamental. Falsifiability, when our dictionary fails. Now, the crucial falsifiability thread. This keeps our understanding honest. If clause labels provide no predictive power for future system evolution, compared to just using the raw phi map, the clause library is not capturing causally relevant structure. We're putting fancy labels on things, but the labels don't help us anticipate what happens next. This means our understanding is an illusion. The library must be revised or abandoned. If the same data stream can be fit equally well by two incompatible clause sets, our model is under constraint. It's like a sentence that could be parsed two completely different ways. I saw the man with the telescope. This ambiguity means our grammatical rules are too weak. We need additional constraints, perhaps from higher derivatives, to uniquely determine the correct reading. If we cannot resolve the ambiguity, our interpretive framework is incomplete. These falsifiers are not threats. They're guardians. They ensure our understanding remains tied to reality, not to our preferences. Lanterns across scales, the universal grammar. This need to recognize clauses is universal. Let's light lanterns across scales. Near scale, the kitchen. Water boiling in a pot. The rising columns of bubbles and the sinking cooler water form smooth jet clauses. The hexagonal pattern of convection cells that sometimes forms is a lattice of coupled constraint clauses. The cell boundaries define a relationship between upflow and downflow. The chaotic bubbling as full boil is reached is a storm of defect clauses. Vortices and plumes constantly being born and dying. A jet stream is a planetary scale smooth jet clause in the atmospheric phase field, where phi could represent geopotential height. A hurricane is a massive, coherent defect clause with a well-defined topological charge, circulation. Weather fronts are constraint clauses, sharp boundaries where temperature and pressure relationships change dramatically, governing wave propagation along them. Far scale, the galaxy. Spiral arms in a galaxy can be seen as wave-like density patterns, wave clauses, propagating through the disk of stars. The supermassive black hole at the center might be seen as an extreme defect clause in the space-time phi field, around which everything swirls. In every case, the process is the same. Measure the field, height, pressure, density, gravitational potential, compute its local derivatives, gradients, curls, and match the patterns against a library of physically meaningful clauses. The physics changes, but the linguistic act of interpretation is universal. The ethics of interpretation, the danger of mislabeling. Here we encounter a subtle but powerful ethic of episode 10, intellectual responsibility in labeling. To mislabel a clause is not a minor academic error. In an engineering context, it is a prelude to disaster. If you misidentify a chaotic, unstable flicker as a stable wave clause and design a control system based on that assumption, your system will fail. It will try to resonate with a phantom and instead couple to the real chaotic modes, amplifying dissonance. The probabilistic safety rail, the confidence score, is an ethical imperative. It forces us to quantify and disclose our doubt. It prevents us from presenting a neat, labeled story when the data is actually whispering, "I'm not sure." Power without coherence is self-destruction. And coherence in understanding begins with the humble admission. I am 60% sure this is a vortex, 30% sure it's noise, and 10% sure it's something else. The engineer who acts on the 60% as if it were 100% is building on a fault line. A measurement scene, the convective cell. Let's step into our roadmap's measurement scene. Scene. We are analyzing the phi field of a convective fluid cell, a Benar convection experiment. A thin layer of fluid is heated from below. Warm, less dense fluid rises in plumes. Cool, dense fluid sinks. A beautiful, ordered pattern of rolling cells can emerge. What we measure? Phi of x, y, t, where phi represents something like the local temperature or density field, or a directly measured optical phase shift through the fluid. From this, we compute omega xyt and k xyt, the pass. Our clause identification algorithm analyzes the movie. It cleanly identifies the rising and falling plumes as smooth jet clauses, regions of strong, uniform vertical phase gradient. It identifies the stable, rolling motion of the entire cell as a pattern satisfying a constraint clause, a relationship between horizontal and vertical gradients enforced by fluid dynamics. Most beautifully, it detects the moment when the pattern reorganizes, when one cell splits into two, and labels the fleeting, unstable structures at the split as defect clauses, pairs of vortices being born and annihilated. Using the clause labels, we predict the path of a rising plume. The prediction is accurate. The labels are stable from frame to frame, changing only when the physical structure itself changes. The algorithm's output is nonsense. Clause labels flicker randomly from frame to frame with no persistence. A region is called a wave one moment and a jet the next, despite the underlying phi field changing smoothly. The labels show no correspondence to the visible, coherent structures in the fluid. The confidence scores are all below 50%. This is a failure of interpretation. The algorithm is lost in noise, or the clause library is mismatched to the physics. The recognition skill, seeing the need for a dictionary. How do you, as a practitioner, know you need this skill? You will look at an evolving phi map and ask, what is that kind of thing? You will stop seeing just a shape and start seeing behaviors. That looks like it's propagating. That region seems stuck in a repeating loop. Those 2 points seem to be orbiting each other. The moment you begin to categorize motions and patterns into types, you're building a clause library in your mind. If you find yourself wanting to draw arrows on a map to show flow, or circles around special points, or dashed lines along wavefronts, you're thinking like an interpreter. The digital twin, training our intuition. Our digital twin is now our language tutor. We don't just use it to test unwrapping algorithms. We use it to generate a vast, curated dataset of pure and mixed clauses. We create a phrasebook. We task the twin. Generate 10,000 examples of a solitary vortex defect moving through a smooth jet. We then train our clause identification algorithms on this data. We teach them what a pure vortex looks like in omega and k, what a pure jet looks like, and, crucially, what they look like when superimposed. The twin allows us to explore edge cases and ambiguities in perfect safety, refining our library and our confidence metrics before we ever point them at messy reality. Enabling the future, from words to messages. This skill, understanding 5 sentences, depends completely on the previous one. You cannot interpret what you cannot read. It requires a clean phi map with honest uncertainty. And what does it unlock? Everything. It enables communication. You need to know the words, the clauses, before you can encode a message using them. To send a command like create a vortex here, you must know what a vortex clause looks like in phi space. It enables programming. A phi program is essentially a recipe for assembling clauses into a desired structure. First, establish a smooth jet. Then, imprint a defect pair within it. Then, move them apart. To write such a program, you must have names for these clauses. This is the bridge from passive observation to active design. We are moving from literacy to composition. Zenodo and the rigorous library. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There, you will find the scientific papers that this audio journey is built on. The papers formalize the clause templates as specific functional forms, or statistical models. They define the probabilistic matching algorithms, like Bayesian model comparison, that generate the confidence scores. They derive the dispersion relations and other constraint equations from first principles of the 5-field dynamics, showing how the grammar of episode 9 generates the vocabulary we're cataloging here. Return to the phi. Let's zoom out. We have taken our second step. We can now read the letters, reconstruct phi, and recognize the common words, identify clauses. We are no longer staring at a mysterious, shimmering landscape. We can point and say, there, a wave travels east. There, a jet flows steadily upward. There, 2 vortices orbit and merge. We have begun to parse the story. We remember, there is only one field. Its evolving story is told through the relationships between its derivatives. Our clauses are simply recurring, stable configurations of these relationships. Resonant patterns that persist because they satisfy constraints. Our understanding is an act of pattern matching against this library of persistence. We have added a new discipline, the pairing of every interpretation with a confidence score, and the obedience to the predictive power test. If our labels don't help us forecast, they are worthless. This is the foundation of dialogue. To have a conversation with the universe, you must first understand what it is saying. So picture yourself back in the observatory. The movie of phi plays on the main screen. But now, an overlay appears. Transparent, colored highlights. A blue ribbon flows upward, labeled Jet 92%. A green rippling sheet moves across, labeled Wave 88%. 2 red pinwheels swirl, connected by a line, labeled Defect Pair 95%. A sidebar shows the confidence scores and the key predictions derived from these labels. You are not just watching light. You are reading a narrative. You have just learned the language's basic vocabulary. You have learned to see the clauses. This is part 10.1.2, Understanding Phi Sentences, the Pattern Library. It is the second branch of Book 10.1, Language Fluency, building directly on the root skill of reading. In our next session, we will take this knowledge and do something evolutionary. We will not just read and understand, we will speak. We will learn to encode our own discrete intentions into a phi waveform that can survive a noisy channel and be decoded. We will move from interpreting the universe's sentences to writing our own. Remember, one field, phi, with its infinite echoes in time, space, and motion. Our fluency grows. We are no longer illiterate observers. We are becoming conversant. Salam, and peace be upon you.